Hi, this is TheoryStation. My name is John Duggan. This is the Rational Choice Modeling Program. The series we're in is Individual and Social Choice, and this is installment number 6 in the series. We've been covering preferences and choice and utility, all thinking about a single decision maker, a rational decision maker, who can order a given set of alternatives. So now what we're going to do is extend the model by having multiple people with preferences over alternatives. And we're going to think about how they can make choices as a group. And so I'll call this, we'll call this installment Voting Rules. We're going to be thinking about these, we're going to have multiple people here. We're going to be thinking about how we can make social choices based on their preferences. So they might be trying to pick, a politician, an office holder from a set of candidates, or they might have preferences over, if it's a group of friends, they might have preferences over which movie to go to or which movie to watch tonight. But we're not going to be thinking about kind of strategic interaction between these individuals at this point. So that said, let's just set up the model now, and we'll start off with our set of alternatives. That's not any different. And before, in the rational choice setup, the model of preference and choice, the next thing I would give would be a ranking of a decision maker. Well, now we have multiple decision makers, and at different points I have to refer to different decision makers. So I need to actually have them in the model explicitly. So I will use pretty standard notation, capital N, for a set of individuals. You can think of them as voters. It's going to be a finite set. We want to be general about the model if we can. So we'll just have any number of individuals here. So let's say that there's n individuals, lowercase n, and we're just going to number them from 1 up to n, okay? So, so if you want to write it out, then n would be this set here, just the first, that is big N, would be the first little n set of natural numbers. Okay, so when I'm referring to individuals, I might be specifically talking about individual 1 or individual 2, but often I just want to refer to some individual without saying exactly which one. And so I will usually use an I. It's called an index. It's basically a variable that runs across those first n natural numbers, okay? So I'll talk about individual I or voter I. Sometimes I'll use a J or a K, but it's just a variable that stands for an individual. Now, before we had a decision maker with a ranking of alternatives, so now we're going to extend that, and we're going to assume each individual has a ranking over alternatives. So we used P before for the strict preference relation of our decision maker, and we'll keep using it. But now these individuals we have might have different rankings, and so I need to have some way of signifying whose ranking this is. So I'll use this subscript I here for the strict preference relation. of individual I. Okay, so that gives me one strict preference relation for each individual. I can actually list those out. I'll have P1, P2, all the way to Pn. And I'm going to enclose that list in parentheses. This is just a mathematical convention. Technically, this is called an ordered n-tuple of preferences, but we'll call it a preference profile. Okay, so or just profile for short. So profile is just a list of the preferences of each individual. Okay, so, and we could also, if we wanted, have a set of feasible alternatives. But that's really optional. We don't really need to have that in the model. And in fact, for this installment, I'm just going to assume every alternative is feasible. So we won't have this y component of the model. All right, so that's the basic setup. And in the rational choice approach, the next step was we wrote down the optimality principle, and we said, okay, so the decision maker chooses the best available alternatives. And here, though, we're going to be thinking about the group making a choice. They have to choose an official to hold some office. They have to choose what movie to go to. You know, maybe there's a budget and they have to choose from, you know, a set of possible public projects. But the idea is they have to make the choice together. The problem is they might have different preferences over what to do. So, you know, how does a group make a choice? Well, there's not really an optimality principle for groups, at least not at this level. So we're not going to go that route. Instead, we're just going to think about different ways a group could make choices. And for now, I'm not going to say one way is better than another. But that takes us into voting. And when we think about voting, we usually think about majority voting first. So let's talk about majority rule here. So the way we're going to formulate majority rule is we're going to think about it as a binary relation. It's a way of comparing alternatives. So you can have two alternatives and then take a majority vote between them to see which one is better for a majority of the individuals. Okay, so we're going to think about majority rule as a binary relation like the P. I'm going to use, actually I think I'll stick with the P, but with the subscript M. So, so this PM is going to represent the outcomes of those majority votes, okay? So it's a binary relation on the set of alternatives, and it's defined as follows. All right, we've defined binary relations before, like when we defined weak preference and indifference, okay? There we started with the strict preference relation, and then to define the weak preference relation, we just had to kind of describe a way of identifying whenever one alternative was weakly preferred to another. So now we just have to explicitly define a rule saying when one alternative is beats another according to majority rule. All right, so how do we do that? All right, so for any two alternatives, we'll say that, let's say x and y, we'll say that x beats y according to majority rule, if and only if okay, so now intuitively we're just going to have a vote. We'll say how many, raise hands if you like x more than y, and we'll say raise hands if you like y more than x, and x wins if it gets more votes. Okay, so the way we are going to write that is like so. First of all, how many people raise hands for x? Well, or who raises their hands for x? This is going to be the set of individuals such that those individuals prefer x to y, right? That's the set of people who would raise their hands in a vote between x and y to vote for x. So who would raise their hand to vote for y? Well, that's anyone who strictly prefers y to x. So the set of individuals who prefer y to x, that's going to be, the people who vote for y. So in majority voting, we count the votes, right? So the number of votes for x is just going to be the number of elements in the set here on the left. The number of votes for y is going to be the number of elements in the set on the right. And x wins the vote if there's more votes for x. So this inequality here is the condition that defines a strict majority preference. So here, just some terminology because I've already been using it. When this holds, we'll say that we can say just x beats y, or we can say that x, I'm going to just start over. Oh, this is just brutal. So who would vote for y? Well, an individual will vote for y if they prefer y to x. So the set of individuals who vote for y is just the set here on the right. So with majority voting, we count the votes. So the number of votes for x is going to be the number of elements in the set on the left. The number of votes for y is the number of elements of the set on the right. And x wins or beats y if it has more votes. So, so this inequality here is the condition that defines when x beats y according to majority rule. Okay, so that's how we define this relation. In terms of well, some terminology, when this holds, we can say that x beats y. That's kind of normal to say that, I suppose. But here, actually, this majority relation we're defining, it has some similarities to a preference relation, but it's not a preference of a particular individual. It's a preference of the group. And so we might say that x is majority preferred to y. And this relation we've defined, I might call the majority preference relation or strict preference relation. So on that note, I want to point out that like a strict preference relation, this majority relation we've defined is always asymmetric. Right? So you can't have this strict inequality going in both directions at the same time. However, we'll see in some examples that it's not always negatively transitive. And that means that it's not a weak order always. It's not always a weak order. It's not always going to give us a ranking of alternatives. So it is different from the preference of an individual. So let's go through an example to see how this works. This example, it's kind of might seem a bit much, but it's one that I want to use later as well. So here I have this table with 6 different rankings, and the way I want to read this is, for this first ranking of alternatives here, the number at the top of the column is saying how many people have that ranking. All right, so sometimes I'll just have like one ranking for each individual, and then I'll just number the rankings. This is a little different. All right, anyway, so there's 18 people who have the first ranking, 12 who have the second, and so on. And the total number of people then in this example is going to be 55. Okay, so so how do we think about majority voting now? Well, we have our definition, and to see how it applies here, I'm just going to create a directed graph. So I have one node for each of the 5 alternatives, and then I just have to fill in the graph. So I have to look at every pair of alternatives and figure out which one beats the other. It's also possible to have a tie, but we don't in this example. And so anyway, this can be kind of a long process if there's a lot of alternatives, because there's lots of different pairs, but that's what you have to do. You have to go through each pair. So let's just pick a pair like A and B. Well, to figure out the majority preference, we count the votes. So who prefers A to B? There's 18 guys there who prefer A to B. Who prefers B to A? Well, there's 12 guys here, 10 guys here. Actually, lots of people prefer B to A. And it's going to win, by a landslide. So, so then we would write an arc from B to A to represent a majority preference for B over A, where B beats A. We could look at E versus B, for example, and count up the votes. So there's 18 votes for E. Here's 9 more. Here's 4 more. Here's 2 more. And then these guys would prefer B to E. But anyway, if we just count up the votes for E, there's 18 votes for E. That's 27, 31, 33 votes for E. And then there's going to be 22 votes for B, and that means that E beats B. Okay, so we could go through every pair like that. I think you get the idea of what you have to do. Let's just skip ahead a bit here and fill in the other arcs in this graph. So E is like that, then D, and then C. Okay. And now we've filled in the entire graph, and that's what the majority preference relation looks like. Okay, I'm using that terminology now of a preference. A couple things about this that I want to point out. If you'll notice here, E, well, actually, let me say this. The majority preference relation is always asymmetric. It's not always negatively transitive, but in this example, it is negatively transitive. And it actually gives us a ranking of alternatives. Okay, what's the top ranked alternative? Well, you can see that E beats every other alternative. That's going to be at the top of the ranking. And then D beats everything except E. C beats everything except E and D, and so on. And the ranking ends up like so. Okay. Now, here, E beats every other alternative. That's a special property. We're going to call alternatives that have that property, we're going to call them Condorcet winners. So E is a Condorcet winner here. A, on the other hand, loses to every other alternative, and so we're going to call it a Condorcet loser. Okay. So let's just define those terms formally. We're going to say it's a Condorcet winner. X is a Condorcet winner if for all other alternatives Y, it beats okay. So X is a Condorcet winner if it beats every other alternative, and it's a Condorcet loser if it loses to every other alternative. All right. In the previous example, there was a Condorcet winner and a Condorcet loser. Turns out that those don't always exist. In fact, when there is a Condorcet winner, it should be pretty clear, based on majority voting, that either will be or should be the choice of the group. Okay, it beats every other alternative. There's an unambiguous choice. If there's a Condorcet loser, based on majority voting, you should never choose it because it loses to everything else. As I said in the previous example, we have a Condorcet winner, we have a Condorcet loser, but there are examples where there is no Condorcet winner, so there is no clear choice. And there's examples with no Condorcet loser. So we'll go through some of those, but before I do that, let me talk about a different way the group could formulate preferences in order to make choices. And this is called the Borda rule. And I'll use this notation P with a subscript B for Borda. So here, instead of just doing these binary comparisons, having people raise hands to see which alternative wins, we're going to tabulate points for every alternative based on sort of where they are in each person's ranking. Okay, so 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 the way we're going to do this is for each alternative, we're going to look at each individual and find a number of points. Okay, so and here we're going to assume that the set of alternatives is finite. We didn't have to do that for majority voting. We can still define this majority relation even with an infinite set, but here we're going to use this assumption of finiteness. All right, so given an alternative x and an individual I, the points for x from I are the following. And I'll use this notation b of x with the subscript I, so we know who the points are from. What we're going to do is we're going to measure how high up in person I's ranking this alternative is. And the way we can do that is we can look at the set of alternatives below x in person I's ranking, right? Because there's only a finite number of alternatives, we can then count that, and we can count the elements of that set, and that will give us a measure of how high up in person I's ranking x is. Okay. If the individuals don't have any indifferences, we could stop there, and that would tell us exactly how high x is in the ranking. And if the individuals, though, have indifferences, then there's a little bit of an issue. Like suppose person I has a ranking like this. Let's say there's three alternatives, A, B, and C. And then another person, J, let's say, has a ranking like this. Okay. Now, if we just tabulate points for B, let's say, in this way, how many points does B get from I? Well, there's one alternative below, so they get 1 point. Person J, on the other hand, B would get also 1 point, but somehow B doesn't look quite as strong for person J, or I'm sorry. In fact, B looks a little better for person J because, sure, there's only one alternative below it, but it's actually tied for first place. Okay, so the point is just that if we compare these two rankings here, you might not want to assign the same number of points for B. You might want to give B more points from person J. And the way we're going to do that is we're going to modify this score. We're going to penalize X for the alternatives above it, like so. Okay, so that is the Borda score for X from I, and the total points for X are just the sum of those. We add up over all the individuals. So this is B of X without an I, because this is the total, and we're going to use the summation notation where we look at the points from person I, and we add those up, going from person 1 all the way up to person N. Okay? And then we define maybe I won't squeeze it in here. And then we define this Borda social preference, or Borda preference, as follows. For any x and y, we say that x beats y, but now in the Borda sense, not the majority rule sense, if and only if it has a higher score. Okay, so so that's pretty clear. Just count the points for each alternative, and then that automatically is going to give you a ranking of the alternatives based on the points. So unlike majority rule, Borda is it's always asymmetric, of course, but it's also always negatively transitive. So that means it's always a weak order. All right, so it always gives us a ranking of alternatives, and that is a I mean, that's a nice advantage of Borda. So there's always going to be a unique, or there's always going to be a well-defined choice using Borda. And if we go back to our example, well, we can calculate points for all the alternatives. And, you know, if you thought calculating the majority relation was a pain, well, this is going to be even more laborious. So, you know, let's just pick C, for example, and do that. For C, we have 18 people with this first ranking. And in this first ranking, C gets 1 point because it's above B, but we subtract 3 because there's 3 alternatives above it. And then there's 12 people with the next ranking, and C again gets 1 minus 3 points. And there's 10 people with the next ranking, and C gets 4 points from those guys. There's 9 people with the next ranking, and C gets 3 points, but it's below D. Let's see, we have, for the second class ranking, C is above A, but below 3 other. And then in the final ranking, C is above 3, but below 1. Okay, so let's just calculate all this stuff. Okay, so we have 18 times -2 and -36, minus 24, plus 40, plus 18, minus 8, plus 4. And what do we get from this? -20, -2, -6 points. Okay, so we could do that for all the other alternatives. I'm going to skip that and cheat a little bit, and what we get is -76 for A, for B, -18, for D, 52, And for E, we get 48. Okay, so then the Borda ranking is going to have D at the top, then E, then C, then B, and then A. So a couple things to point out. One is just an accounting thing. If you add up all these points, you should get 0. The way we're just defining the Borda points, if you add them up over the alternatives, it should just come out to 0. So that's a good way to check that, you know, your calculations are correct. The next thing is that if you look at the choice here for the Borda, using the Borda rule, it's different than using majority rule. So the Condorcet winner was this alternative E, and that's not top ranked, okay? Using the Borda rule, we get D instead. Condorcet winners, if there is a Condorcet winner, it does not have to be the top ranked alternative for Borda, okay? The Condorcet loser was A, and that's still bottom ranked here, but that doesn't have to be either. The Condorcet loser does not have to be bottom ranked for Borda rule. If you're, you know, a bit of trivia, it is true though that the Condorcet winner will always have an above average Borda score, so it can't be bottom ranked by Borda, and the Condorcet loser will always have a below average Borda score, so it can't be top ranked. Nevertheless, we can see a pretty, you know, important difference between Borda and majority rule, and they can, even when there's an unambiguous choice for majority rule, there's a Condorcet winner, the two approaches can give you different answers, okay? One last thing to say here, Borda always gives us a ranking because it's based on points, but you can see that it's harder to calculate. The calculations we did here are using a lot of information. You can't just do pairwise votes. You know, you can't just, to tell if X or Y has the higher Borda score, you can't just ask people to raise their hands, okay? They actually need to give you their entire rankings. So it can just be a lot of work. I should say there's a ton of other different kinds of voting rules you can use. There's a literature in formal political theory and social choice theory that looks at different voting systems. There's some pretty creative voting systems out there, and they can really give you very different results, even though, you know, each one might look completely reasonable. It turns out there just is not really a unique or, you know, agreed upon way of coming up with group preferences based on individual rankings. Okay, so so we've gone through these examples. I think I want to talk more about the features of majority and Borda, but you know, this is going pretty long, so I think it's a good time to stop, and we'll come back to that in the next one, and I'll see you there.